All right, so hopefully you're now on board to learn about the evidence approximations. So let's go over the very first introductory section to talk about what it's all about. Okay, so he's saying in a fully Bayesian treatment of the linear basis function model, which we've been using throughout the chapter, we would introduce prior distributions over the hyperparameters alpha and beta. Remember, alpha was our precision of the weight, so kind of penalty on the weights. And beta was our noise precision, additive noise precision. And make predictions by marginalizing with respect to these hyperparameters as well as with respect to the parameters W. So essentially what he's saying is, and throughout this section, we're going to, this boldface T is going to be our training outputs, but also, and our training inputs are also in here. But he's kind of suppressing them just for clarity. So the idea is, the main idea though is that you want to make a prediction about, see what your uncertainty is about a new value. And again, there's going to be like a little x here, which is going to be your new value versus, and also your, your whole data set of training data that have gone with this, with this t. And so you want to figure out, okay, what's my uncertainty about how, what's my prediction about t for this new value of x. And the full Bayesian way, what you do is you actually just integrate over all of your uncertainty over the parameters of your model. So this was, remember, this was how much we're weighting each of the features, but then also the hyperparameters. So this is the quantity that we're after. So we need to do this kind of big, and it looks like a triple integral, but it's actually more. These are scalar parameters, but W is going to have like, I think it's going to be m plus 1 parameters. Even if for, let's say a fifth order model, maybe you're going to have 6 parameters there, and that's, and then 8. So it's going to be a big integral to do. Nevertheless, this part of the integral we can actually already do. So if we knew alpha and beta, we could actually just do this bit because it's all it's Gaussian. So the problematic term becomes this, and that's kind of what the point of the approximation is. Okay, so although we can integrate analytically over either W or over the hyperparameters, the complete marginalization over all of these variables is analytically intractable. So we can't do this big integral that we need. So here we discuss an approximation in which we set hyperparameters to specific values determined by maximizing the marginal likelihood function obtained by first integrating over the parameters W. So yeah, we'll see what he means by that. And one thing just to keep in mind, I think it's a bit of a problem with kind of Bayesian things. There's lots of different names for some of these terms. So the marginal likelihood is also going to be called the evidence. So, you have to just keep that in mind. We're talking about the evidence approximation, but actually it's also, you can call it the marginal likelihood approximation. Okay. This framework, blah, blah, blah. The main thing about, where this is coming from is notice that it's coming from, the 80s, the 90s, even earlier. And so the point is that people wanted to do this Bayesian stuff since forever, basically, but these integrals are very hard to do. And so they were, and maybe computers weren't fast enough to compute these integrals numerically, so they were after approximations that they could do that would allow them to essentially evaluate these integrals, maybe even get some insight into what's going on. So that's, that's the key thing, is looking at these references. Also, one reference I want to highlight is this one, which is what most of this section is based on. I've included a link to it already, so, and it's worth reading. I think lots of interesting ideas. And I think he is also basing his exposition here on these earlier papers. So if you have time, definitely worth a peek there. Okay, so now let's get into it. So if we introduce hyperpriors over alpha and beta, the predictive distribution is obtained by marginalizing over W, A, and B. So let's just highlight that. That's what we want to do. So that, and marginalizing, just a fancy word for integrating over them. So here we've got how the weights are going to combine with the x's. You don't see the x's here; they're hidden. To get given new t is how how our uncertainty over the weights given our training data and our hyperparameters, and then our priors, well, our posteriors on the hyperparameters given our training data. Okay, here we've omitted the dependence on the input variables x to keep the notation uncluttered. Okay, so if the posterior distribution is sharply peaked, so this is the key, and you have to, in real life when you're doing this, you have to actually go and test this. Then the predictive distribution is obtained by simply marginalizing over W, in which alpha and beta are fixed to their values alpha hat and beta hat. So the idea here is, what we're going to say is, what if we're going to assume that, okay, we're going to say, well, what if P alpha beta given T is approximately equal to delta, two delta functions, so alpha, over alpha hat and beta minus beta hat, right? So let's say we just knew where those peaks were. And if we then substituted that in there, well, you can see that the integration over alpha and beta would then just pick out, had the delta function has this kind of filtering property. So it just picks out beta hat and it picks out alpha hat. And now you've got this integral that you know how to do. So that's the whole idea of this approximation. And this is kind of a general idea, so it's not just about evidence functions, whatever. It's just if you have a tough integral, you might get lucky, and one of your complicated terms, or the complicating terms, not that it's complicated necessarily by itself, you might be able to approximate in this way, and then you get maybe a more tractable integral that you can actually solve. Like in this case, if someone told us alpha and beta hat, we've got an expression, a closed form expression for these predictions. So that's what it's all about. Now the key idea is going to be first kind of looking at this function, which is what we're going to do in the next section, and then maximizing it. So we need to know where these peaks are, of course, but that's the whole idea. Okay, so from Bayes' theorem, the posterior distribution for alpha and beta is given by, well, so here's the likelihood of alpha and beta, and then a prior on alpha and beta. So if, and this is what we'll often do, if the prior is relatively flat, so we don't know, where alpha and beta could be, then in the evidence framework, the values of alpha hat and beta hat are obtained by maximizing the marginal likelihood function. It is also called the model evidence. Okay, so let me just highlight this. This is important. So by maximizing the marginal likelihood function, it is kind of the whole point of what we're going to be doing. So we shall proceed by evaluating the marginal likelihood for the linear basis function model and then finding its maxima. So that's one. That's going to be in the next section, and then, and actually that's also going to be in the next section, finding the maxima. And then this will allow us to determine values for these hyperparameters from the training data alone, without recourse to cross-validation. So we don't have to do this thing where, like, as I said, we pick out W, and then we, then on the training data, and then we use that to and then we adjust alpha on some test set, etc. We can just do all of this, figure out what alpha and beta are, the optimal values directly on the training data, which is very useful. Okay, and recall the ratio alpha to beta is analogous to a regularization parameter. Yeah, so again, whenever you're doing the regularization, you often have to do cross-validation to figure out that parameter. The point is, here we can do it for our model just on the training data directly. Okay, so now let's have a look. Yeah, and one thing I just want to say, in case you've forgotten, it's just because what alpha and beta is. So we've got like the beta over 2. We have some kind of a loss function, looks like phi of weights, whatever, plus alpha. Well, let's just do plus alpha over 2. And so now if you divide everything, we're maximizing this thing. So if you divide by beta, well, this is going to be kind of proportional to 1 and then alpha over beta, 1/2 of alpha over beta, and this thing just becomes like a regularization parameter, just like we've always seen. So that's essentially all he's talking about there. Okay, yeah, now kind of a couple of asides about why to do things this way. So as an aside, it's worth noting that if you define conjugate priors over alpha and beta, then the marginalization over these hyperparameters can be performed analytically to give a student's t-distribution. And we already did this back in section 2.37. The resulting integral over W is still, we have now we're going to have kind of a t, there's going to be some t-distribution hanging out, which is going to be hard to deal with. No longer analytically tractable, it might be thought that approximating this integral, for example, using the Laplace approximation, we'll see what this is, but essentially it says you take some function you're integrating, you again hope that it's peaked, and it's kind of like a Gaussian around its peak. It is based on a local Gaussian approximation centered on the mode of the posterior distribution. Might provide a practical alternative to the evidence framework. However, the integrand as a function of W typically has a strongly skewed mode. So the idea is that you want your kind of function around its peak to kind of look like this, but actually maybe looks like that. And so then trying to model this function with something that is kind of Gaussian, which has no skewness, is going to miss some of this probability. And so strongly skewed modes, so the Laplace approximation fails to capture the bulk of the probability mass, leading to poor results in those obtained by maximizing the evidence. So I think the point here is it's kind of going back to you have this integral, you want to maximize it, and you need to make some approximations. The question is how to evaluate your approximations. And one common way of approximating the integrals is to kind of assume things are really peaked and kind of evenly peaked, like kind of a Gaussian, and then just try to capture it with the volume of that Gaussian. But it turns out, and this is kind of one of the key things, you have to kind of check whether your approximations work. We can always approximate things. How good is the approximation? And so it turns out that that particular approach to approximating this integral doesn't actually work very well. And so this evidence approach is actually, it turns out, it seems to produce kind of a better approximations. But again, you always have to check these things. So it's, come up with the approximation, but then also check it. Okay, returning to the evidence framework, we note that there are two approaches that we can take to maximizing the log evidence. So once we've decided to maximize the evidence, how can we do it? We can evaluate the evidence function analytically and then set its derivative equal to 0 to obtain re-estimation equations for alpha and beta. We're going to talk about that in the section after next. Alternatively, we can use a technique called expectation maximization, a very useful technique. And so we'll discuss this kind of later on when we get to it. So essentially what we're going to be doing in this chapter, in chapter is going to be, so in the very next section is going to be just doing evaluating the evidence function and then just maximizing it. But there are other approaches. And this kind of, I think this again, part of, you see this all the time where as soon as you have to make these approximations, there's kind of lots of ways of going at them. And so and it and they might have different advantages and disadvantages. So again, it becomes kind of up to you as a practitioner to kind of figure out, to try them out, and debug and see what's working, what's not working. Is something too slow, too fast? Etc. Well, too fast is never a problem. So yeah, just keep in mind there's lots of ways of doing these things. That's kind of part of the fun of it too. You can use your creativity to come up with new ways of attacking these problems. Okay, so I think that's enough for this kind of introductory section. The next time we'll pick up with evaluating the evidence function. So hope to see you then.